Okay. So, next we are back again. So, next parallel RLC circuit, right. Look, whenever making it, trying to cover each and everything, it will be helpful for you, right. And just you, I mean, things are very simple, and as it has been taken from the different books are given in that your what you call all the list of the book, and something, it is something my class notes, right. So, something I have tried something of my own also for our understanding. So, any good book you should follow. The books which I have referred there in your this thing, your 4-5 books referred, just see those books, right. All these books are available, right. In your library also all these books will be available. So, now this is a simple parallel circuit, right, RLC circuit. A voltage source V is given, R, L and C, all these things are parallel. So, current flowing through this R is IR, through L, IL and through IC, right. So, so in what we have to do is that is a parallel circuit. So, let us see IR, IL, IC and I, this total current is I is equal to IR plus IL plus IC, right, KCL if we apply here. So, IR is equal to, we are taking this V angle 0 degree, this reference voltage is given. So, a parallel circuit, so V angle 0 upon R, so V angle 0, right, this is the IR. IL is equal to V angle 0 upon JXL. This is your, whenever it will be given like this is your this thing. So, it is actually you will take JXL, right, XL is equal to L omega, right, this is your what you call that your XL is equal to L omega. So, this is JXL we take. So, we take JXL. Similarly, for the capacitor, when we will take, actually it is your what you call, we will take minus JXC and XC is equal to 1 upon omega C, right. This way we will take. Generally 1 upon J omega C will be this thing. If you multiply numerator and denominator, it will be J by J square is minus. So, minus omega C is equal to minus J by omega C, right. So, that is why we write minus JXC and XC is equal to 1 upon omega C, right. So, that means your this one, that V angle 0 upon JXL is equal to V angle 0 XL 90 degrees. So, V upon XL angle minus, we have seen the pure inductive circuit, or what we call current lags, we have seen it. Similarly, for capacitor we see the current leads the voltage, V angle 0 minus JXC. So, it is V angle 0 XC is angle minus 90 degree, because of J minus J it is minus 90 degree, here because of J it is plus 90 degree. So, it will be V upon XC 90 degree. So, I is equal to IR plus IL plus IC, right. So, IR is equal to IR angle 0, because your VR it is pure resistive circuit and this is your what you call V upon R angle 0. So, IR is equal to your IR angle 0, that is IR is equal to V upon R, IL is equal to IL angle minus 90 degree, this IL is nothing but V upon XL, this is the magnitude. Similarly, IC is equal to IC angle 90 degree, IC is nothing but V upon XC, right. So, now if you add, the total current I will be IR angle 0 plus IL angle minus 90 degree plus IL angle 90 degree. So, its magnitude will be root over IR square plus IL minus IC whole square, and angle is minus tan inverse IL minus IC upon R. This is now understandable to you. Therefore, you can write this is the magnitude of the current I into angle theta, and theta is equal to minus tan inverse IL minus IC by R, right. Theta negative, then resultant currents lags the supply voltage if theta is negative, and if it is positive, resultant currents leads the supply voltage, right. So, in general, this is the circuit here in general. So, here suppose in general if it is Z1, Z2, Z3, so it is not pure R, it may be some impedance, some Z1, Z2, Z3. So, I1 will be V upon Z1, parallel circuit, it will be Y1V, I2 will be V upon Z2, it will be Y2V, and I3 is equal to V upon Z3, it is Y3V, right. Therefore, I is equal to I1 plus I2 plus I3, right. So, it will be V upon Z1 plus V upon Z2 plus V upon Z3, right. Therefore, I is equal to Y1 plus Y2 plus Y3V, or I is equal to YV, or Y is equal to reciprocal of impedance, that is called admittance, just now we have seen, right. So, admittance are added for parallel branches. For branches in series, impedance are added, and for branches in parallel, right, admittance are added, right. So, now parallel equivalent, next is, this is a simple thing, right, this is a simple example we took. Now, next is that parallel equivalent of a series impedance, right. For example, this is my series impedance Rs and Xs, and this is my supply voltage V. Now question is that we want this one is equivalent Rp and Xp, these two circuits are equivalent to each other, right. That means Ys is equal to Yp, that means series admittance is equal to parallel admittance, and this branch is Rp and Xp. We have to obtain Rp and Xp in terms of Rs and X. This is your what you call that parallel equivalent of a series impedance. Right. This is series, but we want is parallel equivalent, right. So in this case we know Y is equal to 1 upon Z. So 1 upon Z means for series it is 1 upon Rs plus Jxs, this we define Ys, and this is my parallel equivalent is equal to, we can write 1 upon Rp plus 1 upon Jxp, because this is inductive. So 1 upon plus Jxs, this is we call Yp, right. Or this Rs plus Jxs, you multiply numerator and denominator by Rs minus Jxs, you multiply, and then you will get it is Rs upon Rs square plus X square minus J Xs upon Rs square plus X square is equal to, it is 1 upon Rp minus J 1 upon Xp. This term you multiply numerator and denominator by J. So 1 upon Rp minus J upon Xp, that is equal to G minus Jb. Say G is equal to conductance is equal to 1 upon Rp. So 1 upon Rp is equal to, separate real and imaginary part, 1 upon Rp is equal to Rs upon Rs square plus X square, this one, right. And similarly your 1 upon Xp is equal to Xs upon Rs square plus X square, this is 1 upon Xp. Or just write Rp is equal to Rs square plus X square upon Rs, Xp is equal to Rs square plus X square upon your Xs, right. So that means this is that parallel, your series impedance Rs plus Jxs can be represented by two parallel connecting or what we call impedance. One is of course purely resistive, Rp is equal to this one and Xp is equal to this one. This is called your parallel, this is called your what you call that your series parallel equivalent of a series impedance. This is also possible, right. And we know V by I is equal to say Zs for the series circuit, it is Rs plus Jxs. Therefore V is equal to Irs plus Jixs. So V is my reference thing, and your what you call, this is the current I, say it is inductive circuit. So I is lagging by an angle theta. So this one my Irs and this is my Ixs, right, and this angle is 90 degree, not marking again and again by blue ink, but this is 90 degree. So this is understandable. Similarly for parallel equivalent, I by V is equal to Yp, because it is admittance, that is why I by V, and is equal to 1 upon Rp minus J 1 upon Xp is equal to G minus Jb, right. Therefore my I is equal to, you multiply I by V is equal to G minus Jb, therefore I is equal to Vg minus Jvb. So in that case also V is that reference thing, current anyway lagging by theta. So this is my Vg, so this portion is Vg and this is my imaginary part Vb, so this is my Vb. So both admittance and both impedance, this phasor diagram when you call Irs plus your this thing Jixs, right, that is V, and when you consider your admittance, it will be Vg minus Jvb, both have been shown, right. So now series parallel circuit. So suppose take this example, that is one series parallel circuit. So this circuit actually it is your this point, you have to find out, this is the current I, and this point is A, this is B, this is C, this is D, this point is E, this is F, and this point is G, right. So this is series part and these two are parallel part. So everywhere A, B, C, D, E, F, G it is marked, right. And first thing is these two are parallel, 4 plus J3 and 6 minus J8 it is in parallel, right. Make their equivalent series first, with that you add this one, right. After that you divide V by Z, you will get the I, right. So this is my Fg, so this way it has been marked, right. Your IEF is equal to I, this is I, right, and your Z, your what you call this ZFG, right, this is your F point and this is G point. So you find out that these two are in parallel, this 4 plus J3 and are in parallel, you find out the equivalent. So again and again I will not come to the circuit, but everything is marked. So this is this part impedance is ZAB, this part impedance is ZCD, right, and equivalent is will be ZFG when these two parallel will be taken, right. Similarly for reciprocal will be your admittance. So, again and again I will not come to the circuit. So, you have to find out IF, IAB, ICD, power and power factor. So, YAB is equal to 1. When you will do this, you please draw the circuit first, right. So, 1 upon ZAB, so 1 upon 6 minus J8, it comes this much value. Similarly, YCD, you do it, it will be 0.16 minus J 0.12 mho, right. So, YFG admittance, YAB plus YCD is this much is coming. Now, ZFG is equal to 1 upon YFG. So, it is coming 4.4 plus J 0.8 ohm, right. So, ZEG, now you add ZDF plus ZFG. First what you do, first we compute the admittance of the parallel circuit is easy for calculation, and then we are finding out the ZFG 1 upon YFG. So, this much we got. Now, ZEG, the total impedance will be your ZDF plus your this much. ZDF is given in the circuit 1.6 plus J 7.2 and this one you add. So, it is coming 6 plus your JD, your what you call 6 plus J8 ohm. Therefore, current I should be equal to V upon ZDG. So, this is coming 10 angle minus 53.2 degree ampere. So, power factor is equal to cos theta. So, angle between the voltage and current is 53.2 degree lagging. So, it is 0.60, right, and P is equal to VI cos theta. So, 100 into 10 cosine 53.2 degree. So, P is equal to 600 watt, right. So, next is VEF is equal to I into ZEF. So, the I is equal to IEF I told you at the beginning. So, it is 6 minus J8 into 1.6 plus J 7.2. So, this is your 73.8 angle 24.4 degree volt. Similarly, VFG is equal to V minus VF, you apply KVL, right, then you will get V or what you call VFG, you apply KVL in the circuit. So, I am not going to the circuit again and again, just you draw and look it, you have done DC circuit everything, only consider instantaneous polarity and solve it. So, it will be 100 angle 0 minus 73 point angle 24.4 degree. So, this is coming actually 44.7 angle minus 42.8 degree volt, right. Now, IAB is equal to YAB VFG. So, it is your YAB we got and VFG now we computed here VFG. So, IAB will be this much 4.48 angle 10.3 degree ampere. Similarly, ICD will be VFG into YCD. So, it will get 44.7 angle this one into your YCD, it is coming 8.95 angle minus 79.7 degree ampere, right. And PAB power loss is equal to IAB square RAB. So, it is IAB is equal to 4.48 square and RAB is equal to 6. So, it is 120 watt, right. So, again and again I have not come to the circuit, then it will consume lot of time. I will suggest please draw the, when you look into this video lecture, you please draw the circuit first, right? And all these calculations, other things, if you find any error, you just let me know that whether let me know such that I can rectify myself. Even when I am telling many things, one or two places, because so many things are there, so one or two places I am making small error somewhere, but I have rectified, right, immediately. So, if you have any doubt, you can put all the questions in the forum, I will give you the answer, right. So, whenever you, I tell again and again, whenever you look into this video lecture, first you draw the circuits, then you look what has been done. So, this is my phasor diagram, this is V is the reference one, right, angle 0 degree, and IAB actually leading voltage 10.3 degree. So, that is why it is leading, and your other current, that is your this one, your VFG, that is 44 point, I mean if you come to that VFG, come to this, it is your IAB, that is your what you call, this is leading, and if you come to your VFG, it is lagging from this reference voltage V. So, minus 42.8 degree, that is why this voltage is 42.8 degree, it is lagging, these all voltages are same 44.7 degree. Now, if you think in terms of power factor, PAB is equal to VAB IAB cos theta, VAB 44.7 into 4.48 cosine of this one, because cos theta means angle between your this IAB and this your VAB, this is VFG is equal to VAB, angle between IAB and VAB. So, 42.8 plus 10.3, this is the power factor angle, right. That is why it is taken 42.8 plus 10.3 degree, right. So, it is 120 watt. Similarly, we saw IAB square RAB is equal to 122 watt, that means it is matching. If it is not, that means somewhere calculation, if it is not, then somewhere calculation has gone wrong somewhere, right. So, this is one. Similarly, your PCD is equal to ICD square RCD, it is 320 watt, right, and PEF IF square RF, so it is coming your 160 watt. So total P is equal to PF plus PAB plus PCD, that is 600 watt, right, and power factor your for AB 6 upon root over 6 square plus 8 square, it is 0.6 leading. Power factor for CD part, it is 4 upon root over 4 square plus 3 square, 0.8 lagging. This one you do it of your own, right, and it is given that draw phasor diagram. You please draw the complete phasor diagram, I have not drawn for you, right. So this is your what you call your this is the way, a few examples we have taken, this will solve your purpose, right. So now another one is this problem, your what you call is given to you L1 your what you call L2 your L1 is given 0.106 Henry and C2 is given 37.89 microfarad, CL is your 106 microfarad, L2 is not there, and R3 is there 30 ohm, RL is 50 ohm, right, and this is VL. In this problem you have to find solve for I, I2, IL. Voltage is 120 volt RMS, that means you take the reference 120 angle 0 degree, and frequency here it is 60 Hz. You will take F is equal to 60 Hz. This problem you will solve as standard circuit KCL KVL, this is one thing. Second thing, you will find out, suppose you will find out IL using Thevenin's theorem, right, that you will do using Norton's theorem, you will do this, right, and also using your what you call, and you say you are simply KCL KVL. You should find out all these things, and answers are given, all these things had been asked what you have to do it, and answers are given, right, these are the answer, but per frequency 60 Hz, by mistake do not take 50 Hz, then this answer will not come. So frequency F is your 60 Hz, right. So and all these your what you call, all these answers are given. So all these answers are given. So with this, right, our single phase AC circuit at least this part is over, right. So at least single phase AC circuit is over, and we will solve many problems. Take any book and you please do it. So a circuit, now we will go to the resonance circuit, then you will see the maximum power transfer theorem for single phase AC circuit. A circuit is said to be in resonance, right, in resonance when the applied voltage V and the resulting current I are in phase. When V and I both are in phase, a circuit can be said that it is in resonance, right. So now in that case what will happen, if circuit is a resonance when V and I in your what you call in phase, that means that circuit will become as if it is something like an equivalent or a resistive circuit, right. So thus at resonance the equivalent complex impedance of the circuit consists of only resistance, right. Since later we will see this, since V and I are in phase, the power factor of a resonance circuit is unity, right. Suppose you have a series RLC circuit R plus J XL minus XC, when XL is equal to XC the resonance condition occur, right. We will come to that. Whenever, now this is one general thing, whenever the natural frequency of oscillation of a system could be electrical, mechanical or a civil structure or a hydraulic, right, coincides with the frequency of the driving force, a voltage source in an electric circuit or a wind force in a civil structure etc., the two systems resonate with respect to each other, right. So whenever if the natural frequency of the oscillation of a system, right, if it coincides with the frequency of the driving force, right, then the two systems resonate with respect to each other. Resonance is very, it is not good for the system, right. So in that case your and the maximum and in that case has a maximum response to a fixed magnitude of driving force. So this phenomena is known as a resonance. Similarly for the electrical circuit, particularly the series RLC circuit, when it is a resonance condition the current is maximum, right. We will come to that. Generally two types of resonance in the electric circuits. One is the series resonance, another is the parallel resonance, right. So first we will see the series resonance. So in the case of series is a simple RLC circuit, R J L omega minus J upon omega C, right. So Z is equal to impedance Z is equal to R plus J L omega minus omega C is equal to, you can write say R plus Jx in this form, right. that circuit is in resonance when x is equal to 0. That is, when x is equal to 0 means that L omega minus omega 1 upon omega c is equal to 0. That means L omega is equal to 1 upon omega c. That means omega is equal to your 1 upon root over L c is equal to omega 0. This omega 0 you call that your what you call the resonance frequency omega 0, right. So, since omega is equal to 2 pi f, the resonance frequency is given by f0 is equal to 1 upon 2 pi root over L c, because omega is equal to 2 pi f is equal to this thing. So, it will be f0 is equal to 1 upon 2 pi root over L c. So, f0 is equal to 1 upon 2 pi root over L c. This is the resonance frequency. Now, if you plot, suppose this is my impedance, if this is my impedance, if you plot, so XL is equal to L, this is my Z plot, this is my Z plot, right. Now, this dash line that you are this line, it is XL is equal to L omega, because it is a straight line say passing through the origin, right. Similarly, this side XC is equal to 1 upon omega c, right. This side is omega and this side is your impedance. This impedance means Z, XL, XC, everything, right. So, XC is equal to 1 upon omega c, it looks like a rectangular hyperbola, right. So, that this dash line is plot, right. So, this thing from here to here, from here to here, right, from here to here, this is my XL, and from here to here this is an XC, and at XL is equal to XC, that frequency is equal to this one omega 0, right. So, this is that simple plot for impedance versus your omega. This is omega, this is impedance, right. So, this is my XL is equal to L omega plot, and this line, this XC is equal to this curve XC, your what you call XC is equal to 1 upon omega c plot, and this dash line is the resistance R, right, because at when XL is equal to XC, at that time omega is equal to omega 0, at that time Z is equal to R, because R plus J XL minus XC. So, XL is equal to XC at resonance. So, Z is equal to R. This is my, this dash line is R, right. So, at omega is equal to omega 0, I told you x is equal to x 0. So, the impedance Z is equal to x is equal to 0. So, it will be R. Thus, at the resonance the impedance Z is a minimum, since I is equal, minimum means it is R, because XL minus X is 0. So, impedance is minimum R. So, since I is equal to V by Z, as the Z is minimum, at resonance the current is maximum, right. So, now angle, now theta is equal to tan inverse L omega minus 1 upon omega c R, because Z is equal to your R plus J, it is XL minus your XC, right. So, tan theta is equal to L omega minus 1 upon omega c upon R, therefore, theta is equal to tan inverse L omega minus 1 upon omega c R, right. Therefore, for example, suppose when your at frequency is below omega 0, that is when omega less than omega 0, right. So, in that case, if omega less than omega 0, let me come to this diagram. When omega less than omega 0, this side if you come, if omega less than omega 0, that means this region, right, when omega less than omega 0, the capacitive reactance is more than your inductive side, right, and in other side capacitant reactance is less, but this one will be XL will be more. So, this side if you take omega less than XZ, omega your what you call less than omega 0, right, if this side omega less than omega 0, that means your capacitive your reactance XC, right, is greater than your XL, this side, and this side your what you call when your omega greater than omega 0, I mean this side, right, at that time your what will happen, that X just opposite XL greater than XC, right. So, if you take any value from here, you will find XL greater than XC. So, in that is why in this case that if omega less than omega 0 means that L omega minus omega 1 upon omega c less than 0, that is omega 1 your 1 upon omega c greater than L omega, that is Xc greater than L omega. So, from this condition we get omega your less than 1 upon, it is root over less than 1 upon root over L c, that is your omega less than omega 0. So, all frequencies below omega 0, the capacitive reactance is greater than the inductive reactance, right, and is theta, therefore, theta is negative. So, in that case theta is negative, right. So, if the resistance is low, suppose if the resistance is low, the angle changes more rapidly with the frequency as shown in figure below. Suppose this resistance is very small. So, for very small resistance, this is your omega and this is theta, theta versus omega plot. For small resistance the plot is very sharp, look at that, and for high resistance this is the plot, and this is my omega 0. This side is plus 90 degree, this side is minus 90 degree, right. So, as omega tends to 0, theta tends to minus 90 degree. If you come to that, if omega tends to 0, this term will be tends to 0, but as omega tends to 0, this term will tends to minus infinity, right. So, in this case theta will tends to minus 90 degree. Similarly, when omega is much higher than omega 0, that means if this omega is very large, this 1 upon omega c term is what you call it is negligible, it will be very small, but theta tends to your what you call that plus 90 degree, right. So, this based on that your diagram has been drawn, right. So, now we know that y is equal to 1 upon z, right, that is my I is equal to yv, right. So, because we know admittance earlier we have seen. So, if you plot admittance versus omega, right. So, if your what you call if this is omega 0, this plot is for the higher value of r, and this plot is for the lower value of r. Finally, this dash line where r is very low, it is tending to your what you call to infinity, right, tending to infinity. So, now this is your omega admittance versus omega plot. Other one is shown that impedance versus omega plot, this is admittance versus, and this is your omega 0, right. So, if high r means admittance is low, low r means admittance is high, this is the plot, and if your r is very low, it tends to infinity, right. So, the above plot is also an indication of the current versus omega plot. Now, maximum current occurs at omega 0, because that is at resonance frequency, right. A low resistance results in a higher current. So, the dotted curve shown in the your limiting case that r tends to 0, that means this one when r tends to 0, this is that dashed line, right, or dotted line. So, now parallel, next is the parallel resonance, that is pure RLC circuit. So, in this case this is my R, this is my JXL, and this is my minus JXC, it is capacity. Now, here this R we can date, it is a conductance, these two can be represented as minus JBL by JBC, that is your susceptance, right. So, it is in susceptance, so it will become minus JBL. Here G is equal to 1 upon R, BL is equal to 1 upon XL, and BC is equal to 1 upon XC. I mean, if you take your what you call the reciprocal of this one 1 upon JXL, numerator and denominator you multiply by J. So, J upon J square XL, J square is minus 1. So, that is minus J upon XL. We take BL is equal to 1 upon XL, that is why it is minus J BL, right. So, let me clear it. So, that is why here we are writing minus JBL. Similarly, capacitor will become JBC, it is plus, right. So, BC is equal to 1 upon XC. So, G is equal to 1 upon L. Here for you I have done it, 1 upon JXL is equal to minus JXL is equal to minus JBL, and similarly 1 upon minus JXC is equal to J upon XC, numerator and denominator you multiply by J, that is all, it is JBC. So, admittance Y is equal to G plus J BC minus BL, right, is equal to G plus J 1 upon XC minus 1 upon XL, right. So, that means Y is equal to G plus J omega C minus 1 upon L omega. So, in this case we write Y is equal to G plus JB. So, where B is equal to BC minus BL, right. This is my BC and this is my BL, just opposite like your series one, but we have made it like this considering admittance. So, this is my BC and this is my BL, right. So, this is my BC and this is my BL, B is equal to. Now, circuit is in resonance when B is equal to 0, when this part will be 0, the circuit will be in resonance, right. Therefore, omega C is equal to 1 upon L omega. Therefore, omega is equal to 1 upon root over your LC, that is equal to omega 0, same as before, same as series circuit, right. As in the series RLC circuit, the resonance frequency is F0 is equal to 1 upon 2 pi root over LC Hz. So, if you plot now admittance versus omega, same as your what you call the way we do impedance versus omega for series RLC circuit, for parallel we are plotting admittance versus omega. So, in this case this is my constant, this is my constant G line, because BC is equal to BL, right, and this is omega, and this is my BC is equal to omega, this is dash line, and this is your BL is equal to omega, it is a rectangular hyperbola 1 upon L omega, and this is my your what we call omega 0, the resonance frequency. So, at this point your BC is equal to BL, right, and from this side you can make out when omega less than omega 0, this side, that BL will be greater than BC, right. When you will come to this side, when omega greater than omega 0, right, this side, if you come to this side, it will be your BC your greater than BL, right, just opposite. So, at omega is equal to omega 0, BC is equal to BL, Y is equal to G, right. So, at resonance admittance is minimum, right. So, at resonance parallel circuit, at resonance admittance is your what you call minimum. So, in this case, and since I is equal to YV, so Y is that admittance, the current has also minimum value for the parallel circuit, right. So, now if you plot, now just opposite for parallel circuit, impedance by omega. So, this is at omega 0, so this is at low R and this is at higher R. Just you know, it is something like your what you call that your complement to each other, series and parallel, right. Now, angle of admittance is given by theta, your what you call, this is theta y, suffix is y, capital Y, is equal to tan inverse BC minus BL upon G, right. Therefore, tan inverse omega C minus L 1 upon L omega by G. Now, if you plot this one, this is same as before, this is angle of impedance plus 90 degree, this is minus 90 degree, right. So, this is very high value of R, this is the plot, and for low R, this is the plot, and this is my omega 0. The way we explained the previous one, series one, it is same, but in this case it is your what you call it, that was your, it is angle of impedance, right. So, if you plot like this, it will be an omega C minus 1 upon L omega less than 0. So, omega less than 0, your omega less than 0, and this is your what you call plot. Now, if you see omega less than equal to omega less than omega 0, that is my BL greater than BC. So, theta y is negative, right. So, if you come to this here, your this thing, your this one, right, it is G plus J omega C minus L omega, this is my BC minus BL, right. So, from this condition I say that if your what you call, if BC your minus your BC greater than BL or less than BL, accordingly negative and positive angle will come, right. So, same thing is explained here, that your what you call, when omega less than omega 0 and BL greater than BC, theta y will be negative, right, and if angle of impedance, that means theta is positive, because if it is, this is theta y is angle of admittance. If angle of admittance become negative, then angle of impedance theta will become positive, right. Similarly, if omega tends to 0, the theta y, that angle of admittance becoming minus 90 degree, and therefore, the angle of impedance theta will be plus 90 degree, right. So, when BL greater than BC, that angle of admittance is negative, that means angle of admittance theta is positive, because this is theta y. Similarly, at when omega tends to 0, right, angle of admittance is minus 90 degree, that means angle of impedance is plus 90 degree, right. So, that means at omega greater than omega 0, BC greater than BL, that means theta y, that is positive, right, and angle of impedance theta will be negative. This is just put in that your what you call in that expression, very simple thing it is, and when omega is much greater than omega 0, at that time you will see theta y is plus 90 degree, that is the angle of impedance will be minus 90 degree when omega greater than much greater than your omega 0. That means, if you come to this, that when omega is much greater than omega 0, greater than omega 0, right, then this part is negligible compared to this part, right. That means, in that case angle of admittance is your positive, right. So, in that case angle of admittance is your what you call that positive, now that is 90 degree, and therefore, theta is equal to minus 90 degree, right. So, with this, thank you very much, we will be back again.